We're going to take a look at some molarity concepts that you should be familiar with at this point in the course. Molarity, which deals with all calculations that involve moles per liter or concentrations in solution, encompasses all of the important topics you need to continue on in all future chemistry studies. Taking a look at this first question, the first thing you need to do is figure out what this molecule looks like and then calculate its molar mass or molecular mass in grams per mole. At this point, explaining how to write proper names and formulas is a concept that you would have had to master before a question like this, so I won't go into detail into how the formulas are derived. That is something that you should review yourself. So now what I'm going to do is consider all of the data I have access to. I have a volume, I have a molarity, which remember just means moles per liter, and I also can determine the grams per mole of my compound. So take those three pieces of data and arrange them in order to cancel units effectively. Hopefully we're able to set up the equation like this, recognizing that if you multiply the volume by the concentration, that'll tell you the number of moles of solute in your solution. And then if you continue and multiply by the molar mass, it'll tell you how many grams of that solute you would need to prepare this solution. The calculator gives me this answer, but according to significant digits, I'm going to round my answer off to 261 grams, 3 significant digits. Here's the second problem, and what you should do now is determine the formula of this molecule. The obvious place to go again is to calculate the molar mass of that molecule and then arrange all your given data such that the units will cancel and you'll be able to solve for volume, which we know will be in liters. Please note that there is an error that you'll be seeing on your screen. See if you can recognize it, and at the end of this video I will point it out. You can pause video at any time to go at your own pace. Taking a look here, you can see I started with the mass of solute that would be used. I divided by the molar mass to determine how many moles of that solute there would be, and then I divided by the concentration so that I could figure out the final volume of the solution. 3 significant figures. Again, we're going to take a look at the data that's given. They've given me a mass, they've given me a volume. They're asking me to determine moles per liter. So I'm going to need to find out what the formula is for this molecule and use the grams per mole to bridge the gap between grams, milliliters, and moles per liter. I get this far and realize I can calculate moles, but I don't know how to put the next step in to get the volume incorporated, and I realize that molarity is just moles per liter. In determining the concentration of my lithium sulfate solution, we put molecules in square brackets when we're about to report their concentration. I can just take those moles that I've calculated and divide by the given volume in the question, recognizing that to make it moles per liter, I should divide by 1,000. And when I do that, I will get an answer of 2.38 molar when I round it off to 3 significant figures. That's the final answer. For the next problem, I want to consider the complete dissociation of each of these molecules, knowing that they will dissociate into their ions when they're in solution. So that's what I'm going to do first. Looking at the 100% dissociation of each one of these compounds in solution, I can then determine the concentration of each ion. However, what I have to consider is the following. When I am looking at the volume and the molarity of the chromium sulfate solution here, I have to recognize that when I look at that diagram on the left and notice that I'm about to mix it with sodium sulfate, that will dilute that solution. So I need to do a dilution factor calculation where I recognize that my 300 milliliters of chromium sulfate solution will actually end up in a total final volume of 1200 milliliters. That is the concentration I will be using to determine how much of each ion is in solution. So what you see is my dilution calculations for each of those compounds in solution. This is what we call an M1V1 equals M2V2 calculation, where I know the original molarity for each, I know the original volume for each, and I know the total final volume of the mixture in solution, which is 1200 milliliters. In each case, in black, I have calculated M2, the final diluted concentrations. When I go to report the answers for each ion, I recognize the stoichiometry, which tells me that for chromium I need to double that answer, and for sulfate I'm going to need to triple that answer. In this case here, for sodium, I'll need to double that answer. And here I can leave the answer as 0.810. Just noticing here that my significant figures indicate that I should have 3 significant digits in each one of those values, so 3 significant digits in my answer. So you can see that I'm being very careful to count the number of significant digits throughout. I'm not quite done, because in order to report my final answers, I would recognize that the chromium ion concentration is 0.18 molar. The sodium ion concentration is 1.62 molar. But the sulfate ion concentration, I need to calculate a new final total, because there is a source of sulfate from both the chromium sulfate when it dissolves in solution and the sodium sulfate when it dissolves in solution. And so I need to add those two together for a total final answer that will be reported in 2 decimal places, which happens to work out to be 3 significant digits. And there's my final answer for sulfate. The final question is asking you to separate a mixture of ions that are in solution. It only highlights the positive ions or cat ions in the solution. However, we know that there would be other ions also in that solution, possibly things like nitrate ions or some other ions that are not interfering in the solution. So I need to go to my solubility table and try to find something I can add one at a time to separate the ions from the solution. So I'm looking at the table and I'm trying to find something that specifically will precipitate only one of those 3 cat ions. What I notice is this ion particularly has a low solubility. In other words, it will precipitate with any one of the chloride, bromide, or iodide ions. So that is where I will begin. So I would add chloride ions or bromide or iodide. All 3 are equally correct answers. I would find some soluble compound in the cupboard. I would sprinkle that in. I would notice that a lead chloride solid precipitate would form. And I would then filter this solid precipitate out of the mixture, and now I know that lead has been removed from my mixture. It's important that I point out that you need to separate the solid each time you form it. otherwise, if you don't perform the filtering steps in between, you're not really effectively separating the ions from each other. You'd just be allowing the solids to accumulate together at the bottom of the flask. So in each case, you would filter out the solid and then move on to the next step. So now we're at a place where we've eliminated lead by adding one of those 3 ions. Next, we look to see if there is something I could add which would cause one or the other of the strontium or barium ions to precipitate next. For example, this won't work because both strontium and barium ions would precipitate together at once, so they would not be separated, so that doesn't work. Then I would look, say, at sulfide ion, and I notice again it doesn't work, but for a different reason. This time it's because both the strontium and barium ions remain soluble with sulfide, so adding sulfide would cause nothing to happen, so it wouldn't be an effective result. Next, I look at hydroxide and I notice that strontium is soluble with hydroxide, so that suggests that barium is not. There's my answer. So I would add hydroxide ions in some kind of soluble form, maybe some sodium hydroxide solution. I would filter out the barium solid precipitate that forms. The final step is to determine now how to remove the strontium ions, and I have limitless opportunities here. So let's go find all the correct answers that would effectively precipitate strontium sulfate, in other words, make it be not soluble and form a solid, and thereby I could filter out that strontium from the solution. So all I had left was strontium ions, and I notice that strontium will precipitate with sulfate, which is totally an option because don't forget the barium, I've got rid of it in the last step, so it's no longer an issue. But also strontium will precipitate with all of these. Strontium is considered all others because it is not an alkali. Alkali are these. Step in my procedure is to add any soluble version of sulfate, so perhaps I add some sodium sulfate, or I could add some version of phosphate, or carbonate, or sulfite, and all 4 of those would be correct answers, and so writing out a sample precipitate would be something like strontium sulfate solid precipitate, or maybe something like strontium phosphate solid precipitate. Filter that out, and I've effectively removed each of the 3 ions from the mixture. Now my solution is purified and none of those things are in the water anymore. I wonder if anybody noticed the little Easter egg of a mistake I have in the video here. If we go back and look at this formula, I wrote the formula for sulfate, but it should have been sulfide, but the molar mass I have included there is correct. So my final answer is correct. The typo was in how I represented the formula in my solution.